Let's take a look at stresses under general loadings. So we have a component here, the top diagram here, right? Let's say this is a component under various loadings. We have 4 shown here, P1, P2, P3 and P4. Now, under this condition, these are the 4 external loadings. So if we take a section, and in this case, we take a section parallel to the plane YZ. So that's in this diagram here. If we take a section parallel to the plane YZ through a point Q, so we have a stress element there on point Q, we will have internal loadings acting on the surface, right? At point Q, we will have 2 components. One is a normal component to the surface, so we have delta Fx, and the other one is a parallel force parallel to the surface, and this shows the resultant delta Vz, right? Now delta V is the resultant of the parallel forces. So it is not in the direction of Y or Z. It is at an angle to Y and Z. The delta F here is in the direction parallel to the x-axis, right? So what we then need to do is to make sure that all the internal force components are in the primary direction or in the axial direction. In this case, we have x, y, and z. Therefore, what we need to do is to divide delta Vz into its components in the y and in the z direction. So in the third diagram here, we have one component of delta V is delta Vy, and the other component is delta Vz, right? So we have 2 components for delta V. So in this case now, we have 3 components of the internal forces or internal loadings, and they are all in the axial direction, known direction, or we call it the primary direction, right? And from these internal forces, then we can find the stresses. Delta F will give you sigma x, delta Vy, and delta Vz will give us the shear stresses. So we have sigma x, which is F over A, right? So limiting delta F over delta A will give us the value of the stress at point Q on this surface here, okay? And similarly, delta Vy will give us tau xy, and delta Vz will give us tau xz. Now for the shear stresses, the nomenclature here, the symbol says x, y, right? X, y. Now the first subscript x tells us direction of the plane where the stress is acting. So it says that the shear stress is acting on plane towards x. The normal to the plane is in the x direction, and the stress direction is in the y axis. So it's tau xy. The second shear stress here, tau xz. Now it says that the shear stress is acting on the surface with a normal in the x direction. Okay, that's x there. And z here says that tau, the shear stress, that's z there, says that the shear stress is acting in the z direction, on the plane of x in the z direction. So we find that on this single surface of Q, we have three stress components, sigma x, tau xy, and tau yz. Okay. So if at point Q, we take out the Q element, right? Cubic element in the primary direction, because the primary directions are the one we can calculate using equations in solid 1. Remember? So on the right hand surface, so this is the surface that we were talking about earlier on in the previous slide. We have sigma x. Okay, we have sigma x. We have tau xy, and we have tau xz. So we have three components. So for tau xy, we have a complementary which is tau yx. Okay, tau xy is equal to tau yx. Tau yz, tau xz, tau xz is equal to tau zx. So we have a complementary over here. So these here are complementary. And these here are the complementary shear stresses. Right? So in the other three surfaces which we cannot see behind the stress element, we also have complementary normal stresses and shear stresses. Okay? So on the y surface, this is the y surface on top here, we have sigma y. We can find sigma y if we have all the loadings. And also we have the other shear which is tau yz. And then we have a complementary on the front surface here, tau zy. And then we also have a normal stress sigma z. So those are the initial stress element that we can get from calculations which we have learned in solid 1, right? But then this state of stress can also be transformed, or the value of stresses, in other words, the value of stresses on each surface will change if we change the orientation of the stress element. If we incline it towards a certain axis, okay, we change it, then the stresses on each of the surfaces will change. So we denote here with sigma x becomes sigma x prime, right? So we have sigma x prime. Sigma y becomes sigma y prime because the y-axis now have been rotated as well. And sigma z becomes sigma z prime because the z is also rotated. This is 3D rotation of the element. Similarly for the shear stresses as well, they are now not the same value as the previous given in the top diagram. Alright, so those are the stress element that you learn in solid 1. Now, when we talk about stress transformation is how do we find the values of the stresses when it is not in the original direction. The top diagram is the original direction. So this is the original primary direction. What if we rotate, right? In the bottom diagram, we rotate the stress element. So our problem then, we have two things that we want to find. Number one, if we know the direction of rotation, the angles that they rotate through, right? If we know these angles here, then we can determine what are the final values of the stresses. So in simple words, we say, what are the values for the stress components when the plane is at an angle to the main or primary axis, right? In other words, we want to find sigma x prime, sigma y prime, sigma z prime, and also the three components of the shear stresses tau x prime y prime, tau x prime z prime, and tau y prime z prime. So you'll find that this diagram here shows that it is a 3D problem. Now 3D stress transformation is a complex problem, much more complex than we can cover in this chapter of Solid 2. So what we then see that if, for example, point Q is on the surface of the object, then let's say this front face here is the surface of the object. Therefore, it becomes under atmospheric pressure only, right? Which is very small comparatively with the other stresses. Therefore, sigma z will become 0. Okay, sigma z will become 0. Tau zy will become 0. And tau zx will become 0 as well. If this 3 becomes 0, then we are left with just another 3. Sigma x here, right? Sigma y here. And tau xy or tau yx. They are complementary. This now becomes 0. And this is also 0 because they are complementary to the front shear stresses. So we have only 3 stresses remaining. And that will convert the problem into a 2D problem, which we call plane stress condition. Plane stress. Tegasan SATA. Plane is SATA. Okay. So first we need to understand what is plane stress. Plane stress is a state of stress in which two faces of the cubic element are free of stress. So remember, I mentioned, let's say the front surface here is on the surface of the object. Therefore, there's no stresses on that surface. So similarly, on the rear surface, on the rear here at the back, right, there will be no stresses as well. So we are left with 3 components, sigma x, sigma y, and tau xy, right? So we are left with sigma x, sigma y, and tau xy, which is complementary to tau yx or vice versa. So what we then have is, we only have 3 stresses that we need to define, while the other 3 are 0. Okay? Then you might say, is that all for plane stress? Is it just on the surface of an object? There's another plane stress condition, which is the second diagram here, right? Which is showing that plane stress also occurs in very thin plates with the forces or stresses acting in the mid plane. So these stresses here or forces, right, is acting on the mid plane of the thickness of this object here, which is very thin. Therefore, there's very little gradient, stress gradient occurring within the thickness itself, right? And we have 0 stress here and 0 stress on the other surface at the back. And so this is plane stress condition. Now this is what I have mentioned earlier at the bottom here. The stress element is on the surface of the object, which is not being acted upon by any external loading which is significant apart from atmospheric pressure. So that's the second location where you can find the stress, plane stress condition. This is number 1, this is number 2. Alright. Okay, theta is positive in the counterclockwise direction measured from the reference axis, because theta refers to the angle of rotation. So in this case here, theta is positive counterclockwise from the reference axis. So this is x, that's the reference. So x prime is going counterclockwise to give you a positive theta. If it goes downwards, then theta is negative. So that's minus theta, right? So let's take a look at the triangular element. Now, where does this triangular element comes from? The triangular element will come from the initial rectangle that we have. So we have our rectangular element, right? So if we take a section through, then what we then have is just this triangle at the bottom on this here. So we take a triangular element, right? So that triangular element, if we take this bottom part here, we'll have this x. Okay, original we have x there. So now we rotate it counterclockwise theta and to reach x prime. Okay, the parallel direction is y prime. They are always at 90 degrees to each other. Okay, and before we do our analysis on the triangle, first we need to define the area. Now, the slanted surface is delta A, right? That's the primary area for the analysis. While the vertical surface here, this surface here is delta A cos theta, and the bottom surface here is delta A sin theta. Okay? Okay, so we are going to do equilibrium of forces. So summation of x prime is equal to 0. So we have first is sigma x prime times delta A is this force here, right? Then this is in the opposite direction, the component of this force. Now this force is in the negative x direction. We are taking summation of forces in the x prime direction. Therefore, this force here will have a component in the x prime direction, right? It will also have a component in the y prime direction for each of these forces. So now we have sigma x, delta A cos theta is the resultant, and the component is times cos theta. Similarly, for tau xy, tau xy times delta A cos theta, this arrow here, will also have two components. So it will have a component in the x prime direction and another component in the negative y prime direction. Okay, so it's minus tau xy delta A cos theta, and the component in the minus x prime direction, right, is sin theta. And then this is due to sigma y delta A sin theta, so that's this force here. And the component in the x direction will be that sigma y delta A sin theta sin theta. And then we have the last load here, which is tau xy times delta A sin theta, and the component in the x prime direction will be negative, in the negative direction. So it's minus tau xy delta A sin theta cos theta. So this is the first equation. The second equation that we can find is summation of Fy prime is 0 in the y prime direction. Again, using equilibrium, we can find this second equation here, right? Now we have two equations. They are both equal to 0. So we can rewrite them and rearrange them, okay, to get these two equations here. So we have one which is sigma x prime from summation fx prime is 0. From the second equation, summation fy prime is 0, we get this equation here. Okay. So what do we do next? We have to simplify this equation further because we don't want to calculate cos squared theta and sine squared theta. Okay. So we can simplify that using your trigonometric function. This is from your mathematics. Just use them to simplify the two equations. Okay. And if you replace them and simplify the two equations, we'll get these two equations here. That is equation number 1. That is equation number 2. Now these two are the basic equations which will give you normal stress on an inclined plane, x prime, right? And shear stress on an inclined plane, x prime, y prime. So we will just use these two equations if we want to find stresses on an inclined plane where the inclination is given by theta. So we just replace the value of theta and remembering the sign convention earlier, right? Let's take a look at an example. Now in this example here, we have a stress element which is given, and that stress element is taken on the surface of the fuselage of this airplane here, or in simple word, they are called the body of the aircraft, right? In technical terms, they are called the fuselage of the aircraft. Now, if we take that stress element here, so that's the stress element on the surface, and this diagram here gives you the stress element with the loadings, assuming that the loadings have been calculated or measured, right? So now it says find the stresses acting on the element when it is oriented 30° clockwise from the position shown. So how do you find that? Remember, this is the primary direction. So if we rotate 30 degrees, this is x. 30° clockwise, we are going towards x prime. And that angle will be 30° clockwise. In other words, when it is clockwise from our reference, this is our reference, right? When it's clockwise, theta is equal to negative, right? So theta is negative. Now, if we use the final equation we have derived. However, we can also use our triangles, remember? So the first triangle will be this here, that one here, and this inclined plane. If you take that triangle out, what we then have is, we will have a triangle like that, right? On this surface, we have that 50 megapascal, okay? And the shear stress, which is 25, okay? So that's 25. On this surface, on the left surface, we have 80 megapascal, which is compressive. So we have 80. right? And we also have the shear, which is 225. So now x prime is in that direction, right? So that's x prime. So we need to find what is the value of sigma x prime and also tau x prime y prime. Because if this direction is x prime, then that direction is y prime, right? So finding equilibrium of forces of this triangular element will give us the solution for sigma x prime, tau x prime, y prime. And the next one is this triangle at the bottom there. So you will have another triangle at the bottom, right? Again, we have 50 here, and we have 80 here. Then we have the shear stresses, right? Sorry, wrong arrow. It's to the right, right? So that's 25 and 25. Now in this case now, if that is x, we can call this x prime, no problem. So now let's call this x2 prime, so that we don't confuse with the first figure there. And so we have our stress is sigma x2 prime. Okay, and we can also put this as the positive direction of tau x2 prime y2 prime. However, the angle now is this angle here, right? It's counterclockwise, but this is not 30 degrees. 30 degrees is downwards. This is now 60 degrees. And this 60 degrees is positive, right? So if you remember the directions and the positive directions of the stresses and the angles, okay, the sign convention, then we can use the final equation that we had earlier, or we derive it from first principle, remember, using the equation of equilibrium. Don't worry about delta A. What is delta A value? Don't ask what is delta A, because finally you can just cancel them out. Okay, so here is given the solution. Summation of fx prime is 0. Now if you look carefully in this equation, they all have delta A. That's the area, right? Delta A cos 30, delta A for the inclined plane, delta A cos 30 degrees, and so on, because the angle is 30 degrees here. Okay, so finally from this equation you can cancel out delta A, because every term has delta A. So you don't worry about what is delta A. Don't worry about delta A. Okay, so from this equation you can find that sigma x prime for this direction here, sigma x prime for the first diagram will give you minus 4.15. Minus 4.15 tells you that it is compressive, because we are assuming in the first place it is tensile, right? Similarly, summation of f y prime is 0. We are assuming the positive direction here for tau x prime y prime. And if we equate the equation, we will find that tau x prime y prime is 68.8 megapascal positive. Therefore, we are saying that on that plane there, our assumption is right. So 68 megapascal is positive, upwards on the right hand plane, while the normal stress is compressive, so it's compressive here. Okay, and then we have complementary on the bottom surface. So these are complementary stresses. So we have found the first two stresses on surface AA. Now we need to find surface BB using the other triangle, right? Using the other triangle. Again, you do the equilibrium of forces, and from equilibrium of forces, we'll find that sigma x prime is negative 25.8. Again, our assumption was a positive direction, right? That's the assumption. But the answer is negative, meaning it's compressive. Okay, you can have a look at the calculations. And from assumption of fy prime is 0, we find that tau x prime y prime is positive, because it depends on your assumption, right?